So we're starting today by simplifying radical, bringing back the work that we did from last week in that regard, making sure that we remember the techniques. Now remember, there are two techniques for simplifying a radical. One is you look for the biggest perfect square that multiplies into our number, so like what's the biggest perfect square that multiplies into 20, or you can make the factor tree to break it up into all of its smallest pieces. And if you did that, you might say 2 and 10, and then that becomes 5 and 2. Therefore, it'd be 2 times 2 times 5. Then you can circle the pairs because all the pairs come outside of the radical. So 2 comes on the outside. And then anything not circled, like that 5, that stays inside the radical. That is your final answer, whichever method you use. It would be 2 root 5. The only difference is that if you look for the biggest perfect square that went into it, you would have come up with 4. And so your work would have looked like this instead. You would have said root 4 times root 5, and then the square root of 4 is 2. And the square root of 5, of course, is just the square root of 5. Can't do anything else with it. So either way, you end up with 2 root 5. With that in mind, we can then simplify something that looks like this. A much more complicated looking fraction, of course. And hopefully this particular fraction looks somewhat familiar. If you take a look at your homework from last night, this is the answer for number 1. 6 plus or minus the square root of 20 all over 2. And this is how I expect you to format the answer there. But now we're seeing today that we can actually take them a little bit further. And that's kind of the point of today's work here, is seeing that we can actually break this down more. And the first thing we do is we actually simplify the radical. So simplify the square root of 20 here. So step 1, 6 plus or minus 2 root 5 over 2, because I'm simplifying the root 20 just like I just did. That's why we did that one first. Now that I've gotten to this point, I can now look to see what can I simplify. And in order to simplify a fraction like this, remember, I have to be able to divide every single term on both the top and the bottom by the same number. And so I put squares around, or rectangles around there, each of those 3 terms, because there's 2 on the top. Can we divide all 3 of those by the same thing? Yes, we can. Now, the question might come up, well, what do we do about this part here? What can I and can't I divide it by? Basically, since these are whole numbers out here, you're only looking at the whole number part of it, not the stuff that's inside the radical. So we have to look just at that 2 on the outside. But yes, we can divide that by 2. So since I can divide all 3 terms by 2, I'm going to go ahead and do that. So if I divide the 6 by 2, it becomes 3. The plus or minus is still plus or minus. 2 root 5 divided by 2, it cancels out the 2. And so we're just left with root 5. And then on the bottom, 2 divided by 2 is 1. Well, of course, anything over 1 is just itself, right? So we can actually just leave it then as 3 plus or minus root 5. And we'd be done. That is then a simplified version of the exact answer. So we can actually get it simplified just a little bit further than what you saw before. Now, one thing I want to point out about this, though. Notice I could not start up here by dividing every term by 2. Because that's something I'll sometimes see people do, where they'll do, okay, 6 divided by 2, then the square root of 20 divided by 2, and they'll think that it's root 10. But is that the same? No, right? Because root 5 and root 10, different numbers. So we actually have to simplify the radical before we actually do that division, because I can only divide out a number that's on the outside. All right, so now we're taking a look at how do we know when to use each method, because we've learned all these different methods, but now you're going to start seeing them all mixed up, and the first thing you have to do is decide which one do I use. So we got 3 different methods that we've learned so far. We got the square root principle. That's just a fancy name for you take the square root of both sides of the equation. We have factoring, and we have quadratic formula. Now, this order that I've written it in over here is actually the order that I would suggest looking in. If you can do the square root principle, in other words, if you can just take the square root of both sides of the equation, do so. It's going to be easier than any of the other methods. even if you think you could factor it, even if you could plug it into quadratic formula, if you can just take the square root, it's going to be easier for you. Then if you can't do that, then look to see if it can be factored. If it can be factored, I want you to factor it. It's generally faster, and it's almost always more accurate in the end than quadratic formula, which is your last resort. Quadratic formula, of course, it always works, no matter what the quadratic. If it's a quadratic formula can get you the solution, but as you've seen, it's a big formula. It's easy to make a little mistake in it. So we save that for last. All right, so now as you take a look at each of these three equations down the left-hand side, I'm wanting to figure out which one is going to be used for what. And yes, I do want to use each method once. So it's not like I can just say, well, let's use quadratic formula for all of them. So the first thing I'm going to do is I'm going to look through here for the square root principle problem. Now, do you see which of them we'd want to use the square root principle for? I hope it jumps out to you. Because I can use the square root principle. In other words, I can eventually just take the square root of both sides of the equation if I only have an x squared. If I also have an x in there, I can't just do that. I got to use one of the other two methods. So what I'm doing is I'm looking for an equation where the x only appears once. And you notice that happens in our third equation. So then that must be the one where we are going to use the square root principle. So that's our winner there. From there, well, we actually got to do a little bit of work. It's not so much a just look at it and know kind of a situation, because I need to figure out which of those is factorable. That means we actually have to try factoring it. Now in this case, it's not too bad because the numbers are nice and pretty. Both of these quadratics that we have left start with just a plain old x squared. There's not a number in front of it. So to factor it, we just say what two numbers add to the middle number and multiply to the last number. One of those, there is such a combination, and for the other one, there isn't. Which one is factorable then? The first one or the second one? Good, yeah, the first one. The first one is actually factorable because 3 and 5 would add to 8 and multiply to 15. So since that one is factorable, that's the one that I would use the factoring method for. Well, remember quadratic formula, it is our last resort. And so whatever is left, after we've checked everything else, that one's got to be quadratic formula. All right, we're going to repeat the process that we just went through for this set of problems, where you're going to start by looking to see which one would you use square root principle for. So again, square root principle, you're looking for one where the x only appears once. Because if we have both x squared and x, we can't just take the square root of both sides. So there's only one possibility for that. And that's our second equation. And so that one should be your square root principle. The fact that there's something inside the parentheses doesn't change that fact. We'd still move the 13 and then take the square root of both sides. All right, next up, I need to figure out now which one of the other two is factorable. Now, these are slightly more complicated because they're not just a plain old x squared, it's a 2x squared in both cases. So if I was going to factor it, I'd have to do a times c first. So I'd actually think about what that is. So like in this first one, ac equals 10, and in this one, ac equals 24. So for the first one, I'm looking to see, are there two numbers that multiply to 10 and add to 6? On the second one, are there two numbers that multiply to 24 add to 11? One of those is possible. Which one of those is possible? The first one or the third one? So yeah, that third one is actually our winner. The third one, yes, there are two numbers that add to 11, multiply to 24, 3 and 8. And so, the third one is the one I would use factoring for, which means that that top one, I can't use square root principle, I can't factor it, therefore the only possibility left is quadratic formula. So that's the method we'd use there.